Okay, well, thank you very much. Good morning, and let me first thank the Environment and Health Fund for the invitation to join you and congratulate you on this symposium and the turnout and taking on this very important topic. I also have to congratulate Israel. It seems that you've done away with the tie, which I think is a very good idea. So I'm going to talk about the translation of epidemiological evidence and other evidence into policy. Tell you a little bit about the U.S. Story and what has been happening with a somewhat of a long-term perspective. Now, right now I'm from California. I've been there about 4 years. It's taken me a while to actually say that I'm from California, but I am. And when people think about California, they might think about Hollywood. But if you're involved in air quality, you actually think about other things like smog. And it is in fact in Los Angeles that the phenomenon of ozone air pollution first occurred. And in fact, Haagen-Smit won the Nobel Prize for describing the chemistry of ozone. One of the first great smog episodes was here in 1943. No one knew what was happening. They did not know how dangerous it was. The air was highly acid. Women's nylon stockings dissolved. People wore gas masks. You can see here a smog suit to protect people. We've come a long way. I don't think I would be living in Los Angeles if pollution were as bad as it once was. Los Angeles is not the only place where the pollution was bad. This is the east coast of the United States. In the 1960s, we had these so-called brownouts, large regional episodes of air pollution with levels far exceeding what we would see now. And of course, this is only a decade or so after the London fog of 1952, which killed thousands of people across a week. Now, in thinking about using evidence to make policy, there's a balancing of forces, of what we know, of what we don't know, and then of all those other factors that are important, economics, politics, and they inevitably enter into the discussions and deliberations about what to do. So in sort of a naive way, you might think that what we know should tip the balance, or at least what we know in relationship to what we don't know, uncertainty. And again, there will always be uncertainties. And perhaps that balance figures in to whether we take action, make a decision, or say, okay, more research is needed. Fund my grant. And then, of course, the realities. Politics, costs, activists, advocates, the various stakeholders as they weigh in on the process of decision making. So where that balance falls depends. It certainly depends, hopefully, on what we know in some sort of evidence-based translation process. Now, these ideas do become politicized, and don't ask me to explain what is going on in US politics at the moment, because I can't. And as you know, we only have, 16 hours or something left till we do or do not fall off the fiscal cliff, perhaps taking the rest of the world with us wherever we are going. But it's also been an interesting time for scientists, because I don't think the decision-making process has perhaps ever been as politicized in the U.S. as it is now. Up to figuring in the election, the president himself saying about a year and a half ago that there would not be a revision of the ozone standard. Quite a remarkable story. So the realities are there. But from the scientific perspective, it's this balancing of evidence and uncertainty that is important. Of course, identifying uncertainties is how we chart where research should go. And it is critical to know what we don't know, because those are the gaps that we need to fill in. And it's how we, of course, say what research is needed. And probably many of you have written in the room have written sentences such as, while X has been studied for decades, there are key gaps in our understanding, et cetera, et cetera, et cetera, send money. And this is how we move forward, identifying what we don't know. But in evidence-based decision-making processes, it's important that we get a very firm grip on what it is that we do know. And I'm going to talk about how the US is doing that now in terms of setting air quality standards. We also need to think about what evidence we may need. And if you think about causal questions, a lot of our thinking about air pollution is, well, is air pollution causing adverse health effects? Is it causing childhood asthma? Is it causing people with cardiac disease to die at a younger age than they would absent air pollution? If you go down this list of how you might phrase these questions, does A cause B? Or by how much does exposure to A increase risk for B? Perhaps it's the bottom question that is the one that is most relevant for policymaking, which says, how would the occurrence of B, say premature death, be affected by removing A, removing high levels of ozone, removing endocrine disrupting chemicals, perhaps? So that probably is the question we really want to answer. And I think as scientists, when we talk to decision makers, I think they are really, in the end, interested in this question of, will we make gains in public health? In the US, this has now come to be talked about as accountability. What gains have we made for the regulations, for the reductions in air pollution? A rather complicated question to sort out, but one for which we are developing methods. Now, just to give a little emphasis to uncertainty, inevitably in talking about decision making, uncertainties will be cited, particularly by those who might be regulated, by those who might have to pollute less. They will talk about the gaps in the knowledge. And in the US, our risk assessment frameworks give great emphasis to identifying what are the sources of uncertainty. If you're not aware, there's been an important series of reports from our National Research Council of the National Academy of Science on risk assessment. And I'll be discussing how EPA is using risk assessment in setting air quality standards. But if you're not aware of these frameworks, I suggest that you look at them, and this so-called Silver Book would be a useful starting point on this literature. Along with uncertainty comes doubt about whether we know enough. These books highlight the fact that the creation of doubt has become literally an industry in the United States, and one that has figured prominently in decision making. And I think it would be naive not to recognize that that stakeholders may find it in their interest to say that the science is not sufficient to create doubt. Much of my work has been around tobacco and tobacco control, and the tactics developed by the tobacco industry long ago have been adopted by many others. And for those of you wanting sort of a little bookshelf on doubt, here are just a few of the recent books. And again, these strategies that we see playing out in the US perhaps don't reach elsewhere, but they certainly affect the views that are in the scientific literature. So let's turn to air pollution, and I'm going to give you sort of a long-run perspective from 1950 up to now about what we've done and what we've learned. If you go back and look historically, sort of what I will call serious epidemiological studies on air pollution begin in the early 1950s. That was a time when there had been a number of tragic air pollution episodes. The London fog of '52, before that, Donora, Pennsylvania in 1948, the Meuse Valley, 1933, and others. There was no doubt that high levels of air pollution killed, but there had not been sort of rigorous scientific study. For the London fog of 1952, you did not need sophisticated methodology, multivariate regression, or anything else. You could just count. and the bodies were counted at roughly threefold more per day than there would have been absent the fog. So at that point, there were early surveys comparing the health of people living in cleaner communities with those living in dirtier communities, early time series studies, and the questions were, well, what are the adverse effects of air pollution? Who is being affected? And in these methods, these studies, while crude in their methodology, by current standard, showed damaging effects of air pollution. The modern era, more modern era, I guess, begins in the early 1970s. I think key in the United States and perhaps key for the world was the Six Cities study begun by Harvard in 1974. This was a study of the health of children and adults in 6 U.S. communities that had varying levels of air quality, ranging from very clean Wisconsin, the state of Wisconsin, Portage, Wisconsin, to very dirty Steubenville, Ohio, a town with a steel mill and power plants. The American Cancer Society began its second study of 1 million Americans, one that has been important for showing that air pollution in the long run affects mortality. And at USC, I'll highlight the work of my colleagues who started the Children's Health Study, a 15 community study of air pollution and the health effects on children. These studies were important, particularly the Six Cities study, for launching exposure assessment and thinking about concepts of total personal exposure to air pollution. There were a few surprises. Early on, the Six Cities study and other studies showed that, in fact, particle levels were often much higher indoors than outdoors. Why? Because that great source of particles, tobacco smoking. Levels of NO2 were often higher indoors than outdoors. Why? Because gas stoves and other gas combustion devices not carefully ventilated to the outside were polluting indoor environments with nitrogen oxides. Here, the questions had shifted from what are the adverse health effects to how does risk vary in relationship to exposure. And there was great work, emphasis placed on quantifying risk in relation to exposure to guide standard setting. Then, about 20 years ago, we enter into this era where time series studies were done. Studies in which daily air pollution levels were examined as drivers of daily mortality counts. I think the big surprise here was that, in fact, there were associations. The higher the levels of air pollution, the greater the risk of death. And seemingly, those who we would think would have been affected were the elderly and people with heart and lung disease. And I think the surprise of these studies was that even though air pollution levels had dropped, we were observing these effects. We moved on to carry out multi-site studies. While at Johns Hopkins, my colleagues and I started something called the National Morbidity, Mortality, and Air Pollution Study, a national level study in which we looked at time series within more than 100 cities and then joined them to map out risks across the United States. Later joining with colleagues in Europe and Canada to put together essentially much of the world's, the Western world's, time series evidence. The emphasis had shifted to saying, well, what are the key sources of air pollution? We've driven down levels. Now, what sources should we address? And given the complexity of air pollution mixtures, are there particular components, particular aspects of the mixtures that are important? So over time, emphasis shifted, study methods shifted, and I think we're actually in another moment of transition, and we'll see where we go. Now, what do we do with this evidence in the United States, and how are air quality standards set? So the major pollutants, the so-called criteria pollutants, are regulated under two sections of our Clean Air Act, sections 108 and 109. And I think it's worth your reading the public health mandate of the law. So we set a primary standard to protect health. And it's one, the attainment and maintenance of which, in the judgment of the administrator, based on such criteria and allowing an adequate margin of safety, is requisite to protect the public health. So there's some complicated notions here. We're going to protect the public health, and there will be an adequate margin of safety. We know we can't protect everybody. The Congress knew we can't protect everybody, but we are supposed to be trying to protect almost everyone. For those of you who have heard about criteria pollutants, such criteria actually refers to the scientific evidence, which is to be reviewed every 5 years. So yesterday, in visiting with colleagues at the Technion, I heard reference to criteria pollutants. So this is a peculiarity of the US law. Now, we've had so-called NAAQS, or National Ambient Air Quality Standards, in place since the early 1970s. And this is the first group of standards looked at by where things are today. For example, particles. We were measuring total suspended particles, that is essentially all particles in the air. The primary standard for 24 hours was 260 micrograms per cubic meter, perhaps roughly equivalent to 120 or 130 or so of PM 2.5, or perhaps less, but much higher than what we would allow now. And you can see where the other standards were. So over time, these standards have ratcheted down. In 1987, we implemented the PM10 standard, moving from TSP to a more selected indicator. And then 1997, very controversial at the time, leading to a lawsuit that went to our Supreme Court, the PM 2.5 standard, which was just revised about a week and a half ago. Now, these revisions have been science-driven. For example, leading up to 1997, the time series studies, important work, for example, in Provo, Utah, where the Geneva steel mill opened and closed, and during the time that it was closed, hospital admission rates dropped and particle characteristics changed. But in 1997, there were perhaps 100 or more studies cited by Carol Browner when she implemented the PM 2.5 standard. So here's Carol Browner, Time Magazine, 1997, after implementing both new ozone and PM 2.5 standards. But over time, the standards were science-driven. The process rested on review of the scientific evidence and the setting of standards that were evidence-based. And again, this is Lee Thomas, administrator, in 87 with the PM10 standard, then Carol Browner in 97. And here is my quote that I now adapt in different ways, saying there are gaps in the science, that the science provides a warning, and in fact, it was that warning and indication of adverse health effects that led to the standard revision. So over time, we have made tremendous progress in the United States. This is how levels have dropped in relationship to the national standards, this 1980 to 2006. And you can see that in general, the levels have continually dropped in relationship to the standards. We have made progress. Previously, landing in Los Angeles, you would descend into a cloud of smog, eyes would burn, throat might be irritated, and now that rarely happens. I remember visiting LA and realizing that there were mountains right at the edge of town. They had been invisible literally for decades on most days of the year. So air pollution has improved. I'm going to show you 3 papers that I've been involved in doing epidemiological research over time. This paper from 1981, that's a long time ago, was one of the first time series studies of emergency room visits and hospitalizations in relationship to air pollution. This is actually Steubenville, Ohio, which had a steel mill at the time. And here are the levels of particles and SO2, very high by contemporary standards, ranging up to 700 micrograms per meter cubed. In other words, a cloud of particles. In 1997, we reported on a reanalysis of air pollution and mortality in Philadelphia. Philadelphia had been extensively studied because of the availability of a long time series of data. And still, TSP levels rather high and ranging up to several hundred micrograms per meter cubed. Then, most recently, we published use a cohort analysis looking at premature mortality and fine particles, PM2.5, in participants in our Medicare system, and talk about where things might be going. We assembled a cohort using administrative records of 13.2 million people. And then we followed those people for mortality using Medicare records. We used address to link them to estimated pollution exposures at their residences. Here are the levels, PM2.5, and you can see how low they are compared to where levels had been. So in fact, one of the challenges for epidemiologists and for regulators has been the narrowing of the range of exposure and the reaching down of our research. Let me just lay this out for you real quick. Between the irreducible natural background or policy-related background of air pollution, the pollution coming from nature and from long-range transport that can't be addressed through national level actions, and what we are studying. So in the United States, we have come down progressively and are looking at pollution at lower and lower levels, such that the range between natural background and what we're studying is becoming very narrow, really complicating decision-making and forcing a lot of the decision-making towards thinking about technical feasibility. A further dilemma comes from the fact that we are, even though air pollution levels have dropped, still identifying adverse effects of pollution exposure. And this has really shifted emphasis in the United States to using risk assessment to say, if this is where we are and this is where we could go, how much disease can be avoided by different standards that might come in at different points. So risk assessment has become very important in our standard setting process. There's also, I think, been an important emphasis on mechanisms of disease. Epidemiological evidence cannot really address whether there are thresholds at lower and lower concentrations. And with more restricted ranges of exposure, it's more difficult to describe dose response. So I think there's an important emphasis on mechanisms and what processes may be in play at different levels of exposure. We are giving great emphasis still to describing exposure response and searching for thresholds. This plot shows an analysis of dose response based on approximately 50 studies using Bayesian statistical methods to sort out whether there is indication of a threshold. Here the answer is no. So turning to where we are now, for PM, and I think roughly the same might be said for ozone, we have a very large body of research evidence. And I think one question for you will be, what do you need at the national level to understand the relationship of your particular exposures to this very large body of evidence developed externally? We're still seeing adverse effects at levels at current urban levels. I think one of the big surprises has been the very large body of evidence on cardiovascular disease, most recently summarized in this statement from the American Heart Association. We're still struggling with what aspects of particles may drive risk. Now, noting that I only have 10 minutes left, I'm now going to give the next 30 minutes of my talk. Uh, I want to tell you a little bit about what we are doing in the U.S. in terms of an evidence-based process. This is how the U.S. is currently setting its standards for the so-called criteria of pollutants, the National Ambient Air Quality Standards, or NAAQS. So the start, of course, is science and scientific evidence. The agency assembles that evidence into something called the Integrated Science Assessment, or ISA, a fairly large volume, perhaps 600-700 pages, bringing together what we know, giving emphasis to the most recent findings. That becomes the foundation for doing what is called the risk and exposure assessment. It is here that risk assessment is used to say what are the risks of air pollution using indicators of morbidity and mortality identified through the ISA. This risk and exposure assessment becomes the basis for the policy assessment, where the agency considers alternative standards and what risks might be avoided under them. There's a process of scientific peer review by a committee called the Clean Air Scientific Advisory Committee. I just finished 2 terms as chair of that committee, and this is one of the critical points of scientist-agency interaction. Then, after the policy assessment, there is a continuation of the process through the agency and the executive branch of the government. And I'm just going to run through this very quickly. If you're interested in seeing these documents, you can go to the EPA website and either under the Clean Air Scientific Advisory Committee or under particulate matter, find these documents. And the last revision of these documents was in 2010 for PM. And we are, in fact, just doing the review of the ozone evidence at this time. So the ISA, this is the review. It gives emphasis to causation and whether there are effects, what effects are causally linked to air pollution, and describes the strength of the evidence. Like any systematic review, it has evidence tables and plots. And these documents are developed over roughly a 1-year time frame and go through multiple revisions before being final. They list, as you can see, levels, strength of evidence, causal, likely to be causal, inadequate, and so on. And it is those effects for which the associations are found to be causal that are given the most consideration in the risk and exposure analysis and the policy assessment. So lots of that. The risk and exposure assessment, as I said, describes the risks. And again, here it is, another lengthy, complicated technical document. A lot of complicated analysis based on both atmospheric modeling and exposure modeling for individuals. And EPA has developed increasingly sophisticated tools. They do case studies for key urban areas for particles. And again, here is a description of the risk assessment approach that is used. It draws on monitoring data, epidemiological studies, time activity data, and in the end comes up with risk estimates describing the risks under current air quality standards and other alternatives. And lots of tables in it describing what happens in different locales. And conclusions, and then finally the policy assessment. The policy assessment now is going to say, here are the risks. If we set standards, different pairs of standards, short-term, long-term, how much disease could be avoided, how much morbidity and premature mortality could be avoided. So this is the policy assessment, and again, written by the EPA staff, peer-reviewed by the Clean Air Scientific Advisory Committee. And again, tables, figures. This plot, for example, shows how air pollution, various scenarios of control would reduce disease. Here's the percentages in the urban case study sites. And again, I won't go into the detail, but just point you to the process. Scientific evidence on risks, estimation of population risk, and then is shown here consideration of how much public health burden could be avoided under different scenarios of regulation. So it's simple in concept. The details, the technical details, are far more challenging. So then conclusions and recommendations to the administrator. Okay, so in fact, wow, I'm almost on time. So in fact, this story just ended for particulate matter, and EPA, in fact, tightened the PM 2.5 standard. There are two primary standards. There is a 24-hour standard, and there is an annual standard. EPA tightened the annual standard, moving it from 15 micrograms per meter cubed to 12 micrograms per meter cubed. Now, the implications of changing the standard are that some areas of the country might then not be compliant with the new standard. And if you look at, let's see, let me just take you back. Here's a map of areas that will not meet the new standard. And as you can see, Southern California lights up, particularly some of the Central Valley, the agricultural areas, Los Angeles, and then other parts of the nation. Now, most other parts of the nation are anticipated to be in compliance by the time they have to, but Southern California will persist in being out of compliance. Had there been a tightening of the 24-hour standard, I think it's likely that more areas would have been out of compliance. So here are the recommendations then for the new standard. And I think it's important to point out that the evidence base here is clear. It's assembled in the ISA. It goes through a relatively transparent process, and one that I think is important. Now, I really am almost done, and according to my watch, I have 3 more minutes, which is the official watch. No, we will. We'll get there. So I just want to just finish off a few points. So PM, current levels of particulate matter are still associated with adverse health effects. I think this is a real dilemma for the regulators. I think what is also clear is that there are many parts of the world that just have unacceptable PM levels by all guidelines, whether it's the EPA standards or the WHO guidelines, which are guidelines but offer tiers to have some targets for the lower income countries. And I think what research is needed to solve these kinds of problems is a bigger question. This is a problem that has to do with infrastructure, economic development and growth, and many other issues. This problem, of course, has received great attention, high-level exposure to biomass. And certainly if the air looks like this, you don't need too much research. I happened to be in Delhi when there was an air pollution episode severe enough to get to the front page. So this was quite remarkable. So there's many challenges ahead, and I think for some, scientific research is needed, but it's not always the case that more research is needed. Thank you.
Thank you very much. We have time for 1 or 2 quick questions. David, please.
Thank you for the nice presentation. I'm David Katoszewski from BGU. These days, the measurement systems can look at particles of several nanometers. And even though it's not this scenery, they are very dangerous. And in Europe, next year, there will be the Euro 6, which will take into account nanoparticles, a size distribution looking at the number of particle number. And how this is going to be in the US. looking at both vehicles and combustion.
Yeah. So it's an important question. I have to say, from '98 to 2004, I chaired a National Academy of Sciences committee that set the agenda, the national agenda on particulate matter research, and we put a great deal of emphasis on particle characteristics, including size distributions. The EPA in these documents actually did review the data on so-called ultrafines, or particles less than 0.1 in aerodynamic diameter. And clearly, traffic exposure brings a lot of, can bring very fresh vehicle exhaust exposure to particles in very small size ranges on the short term. I don't think in terms of moving to either particle number-based standards or let's say a PM.1 standard, we have the scientific basis. We actually don't even have the measurement base for doing that right now. There's not a reference method for PM.1. These particles are very complicated to both collect and analyze in that size range, and as you know, the monitoring equipment to do size-based particle counts is quite complicated. I think we, on the other hand, need to develop a research base that will allow us to better understand those exposures and their health implications. And I think need to move from things like how distant one might be from a roadway to better understanding what that means. So while I think this is a clear case for more research is needed for sure.
Thank you very much. I want to thank the speakers. Thank you very much.